Hi, my name is Grace Muka, and this is my Lab 3 report for Physics 2211, Mass of a Black Hole. Over the course of this lab report, I will go over the goals of the lab and physics principles and formulas used within the lab. I'll show my GlowScript code for the lab and show how I found the black hole mass as 9.995 times 10 to the 33 kilograms, and how I found the initial velocity for the spaceship to get close enough to the black hole without crashing and then being able to leave the system to be 8.18 times 10 to the 6 meters per second. I'll also discuss my observations and considerations for the what-if questions of Lab 3. The goal of Part 1 of the lab was to find the mass of a black hole, while the goal of Part 2 was to fly around and get close to the black hole, to observe it without getting sucked into the black hole and without crashing into the orbiting planet. For Part 2, the formulas and concepts we used were as followed. We know that momentum is mass times velocity, and that the change in momentum over the change in time is equal to the net force. For non-constant forces, F net parallel and F net perpendicular add up to equal the net force. We can use this equation in other calculations by further expanding on it. The gravitational force formula tells us that the force of gravity is equal to negative g big M little m over r squared times r hat. The velocity update formula tells us that the final velocity is equal to the net force divided by the mass times the change in time plus the initial velocity. In terms of formulas and concepts for Part 2, we need to know about the force of gravity for both the planet and the black hole, and how to calculate and apply that using formulas discussed for Part 1. This is my code for Part 1 of the experiment. I inputted my email so I was able to find a unique mass of the black hole. I also inputted the given star mass for the lab and made delta t one day using seconds through this calculation. I edited the lines of code, including applying formulas to calculate momentum and changes in velocity and momentum. I applied the formulas that I previously discussed to calculate the parallel and perpendicular components of the net force, and I also added lines here and used my formulas that I discussed to find the mass of the black hole, which I found to be 9.995 times 10 to the 33 kilograms. These are my visual and numerical results from Part 1, and as you can see, the mass is shown here. This is my code for Part 2 of the experiment. I changed the black hole mass to match mine that I found from Part 1, and I implemented formulas here to find the initial conditions and velocity here for the ship. I found this using trial and error, especially with the constant I multiplied the y speed component by. I used the information from finding the net force previously in the code and applied Newton's second law in the position update formula to find the next positions and velocities of the ship using the code shown on the screen here. These are my visual and numerical results of Part 2 of the lab. As you can see, there were some issues where the spaceship got out of orbit, so that is accounted for as a possible error in the lab. For Part 1, the system was the black hole and the surroundings were the star, and for Part 2, the system was the spaceship and the surroundings were the black hole and the planet. Some possible sources of error for the lab could be wrong approximations with the constants, and error with guessing constants for equations for the speed of the ship. In terms of how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components, mathematically they're the same, however they have different meanings. The rate of change of momentum can be observed using velocity and mass to find the momentum over time. It describes the system's behavior. The net force is the change in momentum over the change in time. It describes the effect on our system, which could affect our system's motion. Therefore, the net force is equal to the change in momentum over the change in time, but the meaning of each component in the equation varies. To take a quick look at the black hole and leave, we would need to enter an orbit around the black hole with an initial velocity with an x component of negative 9 times 10 to the 6 meters per second and a y component of 10 times 10 to the 5th meters per second. I used my GlowScript code to find these values through guessing and checking, and this was the resulting visual output.